today's CCS forum. We are very excited to starting to live stream these sessions, and they will also be available to watch later on the CCS YouTube channel. So check it out. There will be more contents coming in the near future. But today is, I think, our first forum for a while at least that we are adding to the channel again. And I'm very excited to introduce our presenter today. Noah Evans is a PhD student, actually in my group. He started his PhD this year. Previously, he worked with us as an undergrad researcher. He completed his undergrad in civil engineering here at the University of Florida and is now pursuing also a PhD in civil engineering with an emphasis on coastal geotechniques. And he will talk to us today about a really relevant topic here in Florida. And he's looking into the role of carbonate shell hash on beach sands. So thanks for being here, Noah.
Thank you for having me.
And I think at the end, he will also speak very briefly to the student club. So for everyone who's not familiar online about what the CCS student club is doing, he will speak a little bit about that as well. So welcome, take it away.
Well, thank you for that wonderful introduction. So like Nina said, I'm here today to talk a little bit about the impact of shell calcium carbonate on geomechanical properties of beach sand. Just a quick thank you to Nina and Steven, my co-authors on this, and for all the help and the work that they put into this. Okay, so to give a little bit of background on why this issue came up and why this is something that we're actually interested in, this started as part of the project looking at intertidal rock outcroppings and how these features on beaches can impact the soil and the sediment movement along these beaches. So one of the big things that we noticed when looking at these features is that they accumulated this shell hash, and this presence of shell hash was something that we were interested in, looking at how along the beach spatially and with time, how this then impacted the overall geomechanics of the beach. So to do this, we started with a collection of samples and some in situ testing. And then we took the soil and we brought it back to the lab and did some index testing and some strength testing to get some values. And I'll talk a little bit about that later. So kind of going into the location of it, we are at a quartz sand beach in Flagler Beach, Florida. This has a large presence of shell calcium carbonate shell hash. Now, shell hash for this general presentation is defined as anything that is made of shell calcium carbonate. So this will be larger shell pieces, but then also the kind of smaller grains that get crushed and broken down with weathering and with time. This beach has a semi-diurnal tidal cycle and has about a 1.1 meter mean high tide, or tidal range, sorry, and has a relatively kind of medium tidal range or tidal zone with about 30 meters wide and a relatively small slope of about 5.2 degrees. So a little bit of a background for anyone that's not super familiar with geotechnical engineering or soil engineering. When we talk about soil, we typically talk about it in two parts, and that would be our void and our solids. Now, our void is made up of our air and our water, and the solid is made up of particles. This will be anything that is solid in the soil. So when looking at the soil, we are interested in the density as well as the unit weight of the soil. This gives us an idea of how the voids are, what the compaction of the soil is like, how water can permeate through it, and generalized, it can be used to then infer strength. For this specific topic, we did a direct shear testing of the soil to get an idea of its shear strength, which can be related to erodibility in a further study. So at the actual beach itself, when we went there, we set out two cross-shore transects. Each one was approximately 30 meters long. We started at the dune and went down to the intertidal zone, as you can see kind of represented here in the bottom. And these were spaced at 5 meter intervals. These points were surveyed at low tide to give us the widest tidal zone that we could get. And At each location, we collected 10 centimeter core tubes, and we also took in situ moisture content reading. Now, this is volumetric moisture content. Now, once we get the samples back to the lab, the first thing that we're going to do every single time is index testing. And to start with this, we start by weighing the core samples and getting an idea of the wet density of the sample, as well as the unit weight of that sample. These samples are then dried so we can get a gravimetric water content. From there, we can relate our wet density to a dry density, which we will be using later when we start the testing. We then dried the whole sample, conducted a sieve analysis. This gives us an idea of the grain size distribution of the sample. And then for this specific topic, because we wanted to know about the calcium carbonate content, we used a 5 molar HCl to dissolve this calcium carbonate and get an idea of what kind of proportion of the solids it composed of these samples. So when we started with the strength testing, the first thing that we did is we chose samples to represent our sand, our pure sand. So these are samples where we dissolved all the calcium carbonate out, and that was our pure sand sample. Then from each transect that we took, we selected 3 samples from along these transects at relatively equal spacing. And these were essentially our strength testing samples. They were tested at a unit weight of 16 kilonewtons per meter cubed. And this was because when we actually did our dry density and our dry unit weight, it was significantly smaller than we expected. And so we had to actually increase the package or compaction of the samples to actually get reasonable testing results. These subsamples were then normalized to shell hash percentage. So essentially what we did is we took each sample, we weighed them out, ensured that each one had the correct amount of kind of larger shell hash relative to the whole sample, so that we would get a generalized idea that they were representative. And then for the testing, we started on a lower end to kind of use low normalized stress to mimic the beach face sediments, so that we actually have an idea of, again, we're applying this to something real. For anyone that doesn't know, when we do soil shear testing, essentially what we do is we take the soil, we put it in like a cylinder, then you put that cylinder in a box, you apply a normal force on top of it, and then you displace it horizontally. And then the resistance is what you are measuring from the displacement and how the displacement changes with time. So getting into the results, the exciting part, let's start with the in situ moisture content. So again, this was part of the field exploration. So starting at the dune at 0 and going towards the water line, that's closer to 25, we saw a general increase in moisture content pretty much all the way down the beach from the dune to the water line until we hit about that location about 5 meters from the water, where we actually saw a decrease in the moisture content, which was a little puzzling to us at first, because that's not what you would typically expect, right? As you get closer to the water, you'd expect actually that your water content would increase when you're measuring it, which we'll get into a little bit later. Looking at our shell hash content, we see a increase as we go from the dune to the water line, and actually it keeps increasing. So unlike the moisture content, it doesn't dip at the end, it actually continues increasing. And we're actually getting up to over 60%, where the shell hash is kind of becoming the majority of this sample. For our grain size distribution results, we sieved before and after removing shell carbonate to get an idea, okay, what part of this sample is made up of shells, and how do those impact how the grains are distributed and what we have. So we took the D50 for each of these samples at each of these locations. So the D50 is your median grain size, gives you an idea of the average grain size. And then we took an average of all of those samples along each transect for comparison before and after. As you can see, our mean D50s decreased once we removed the shell hash. This kind of tells us that the shell hash is actually making up a larger portion of the grain size, which, going back to where we talk about soil and solids versus voids, this means that this impacts how these soils are packed and how they're composed. So for our direct shear testing results, the main thing that we're looking for is our peak shear stress before failure. So once we load up the test and we apply our normal force and we apply our displacement, there's a point where we see a failure. And what we're looking for is the shear stress at that failure. And we want that shear stress for each one of our normal forces applied. So as you can see here, circled in red, this is our peak shear stress failure for our 78 kPa normal force. For our first transect, T1, which did not include presence of hard bottoms, we see a maximum shear stress or a peak shear stress kind of floating around that 50, maybe up to 55 kPa for our 78 kPa. But for the most part, these look pretty similar. Getting into our transect 2, pretty similar as well, where we're seeing this kind of peak shear stress around 50. Actually, these ones are going up closer to 60. And this is what we will use then to compare it using what I'll explain next, which is our Moore-Coulomb failure criterion. So this is a way that we can describe the shear strength of the soil using the cohesiveness of the soil and the normal force applied to it, as well as the internal friction angle. So because we're working with sands, our cohesion is usually considered negligible, which we considered in this case. And then to calculate our internal angle or our internal friction angle, what we wanted to do was use our peak shear stress and our normal stress applied, and then plot those against each other and graph a line of best fit. Now, as you can see from the figure, our friction angle is actually the angle between our x-axis and our line of best fit. For these samples, what we would usually expect for a solid sand is somewhere in the low 30s, 32 degrees about. So these results are relatively what we would expect. Now, the really interesting part was that our samples that had this shell hash material actually showed higher peak friction angles than our samples with less material. So as you can see, as we're increasing the shell hash material in the samples, we're actually seeing a larger peak friction angle. And down here, all the way in the left, in the bottom corner, the black one, that's our only quartz sand. So that's no shell hash. So as a whole, what we gathered from this is that our grain size distribution is impacted by the shell hash in a positive way, where our D50 actually decreases with less shell hash. Sorry. And then our large pieces increase the grain size distribution, D50. For the moisture content, we noticed that it might be regulated by the presence of shell hash. This is likely due to the fact that it creates larger voids and allows for better drainage of water. But as we saw, once we got shell hashes over about 60%, we started to see the moisture content decreasing. We also saw a positive correlation between the shell hash content and the friction angle, suggesting that the samples with the shell hash are less susceptible to erosion and are more resistant to erosion because they can withstand higher shear strengths. So to go into this a little bit further and what we need to do for the future to actually kind of flesh out this study would be to look at more grain size versus shell hash. So looking at the actual grain size of the beach sand and wondering if, or figuring out if what we're seeing, these effects are actually because of the grain size difference or if it's actually because of the properties of the shell hash. Additionally, we would like to look more into the correlation between the shell content and peak friction angle. Again, to make sure that it's not just the size of the shell hash, but actually the properties of the shell hash. And then looking at how the shell hash will impact porosity of the soil. So I would like to first thank the Office of Naval Research for their funding, as well as the field people and field staff for the UF Center for Coastal Solutions. And thank you to everyone who attended today's presentation. Additionally, I would just like to point out, it's actually not upcoming anymore, it is published. But my co-author, Stephen, was the main author on a paper that goes a little bit more into the impact of hard bottoms on shell hash accumulation. And so I think it's really good to partner with this, and it's got some very interesting information. Okay, and that's it for my presentation.
Maybe we go into a questioning round.
Yeah, that was great.
Well, we are going to to talk a little bit about the student club. So questions from the audience.
Yeah.
I don't know if you mentioned that and I just missed it. The pure quartz sand, is that what you got after the salting, the shells?
Yeah, so what we're calling the pure quartz sand is the sand sample after we use HCl to dissolve out the shell hash material. And for that, we actually also removed the large shell hash pieces with a sieve beforehand, and that kind of sped up the dissolve process. I think that's fun. Thank you.
What's the nice talk? No,
Thank you.
learn more about your research. What's the source of sand? Is that how much? I guess what I'm getting at is like how much of this is from beach nourishment and is brought onto the beach from offshore?
Yeah, that's a great question. Flagler, I know in the past has had nourishments, so I wouldn't be shocked if a proportion of it was. However, from what we're understanding and from what we've seen, the shell hash is likely naturally put there from kind of the hydrodynamic forcings along the shore. Right.
Okay. And can you, I'm curious, and I'm sure this is like a topic of conversation given the research interest in the lab, but because I was thinking, I guess it's Flagler's maybe different, but I know a lot of beaches in this vicinity, like people drive on the beach.
Yeah.
And I'm wondering like how the shell like given, because I don't understand that like the interpretation necessarily of like the stress testing you did on the sand, but how does that translate to like drivability? And
That's a great question. Yeah.
I know this. I know. I mean, I know.
Yeah,
you guys are thinking
no,
about
I
this
just
stuff.
heard another presentation
Oh,
from
that's
Stephen.
right. So, yeah.
Drivability model sense. Yeah.
Yeah, so Stephen is doing a lot of that's one of his main focuses, the trafficability assessment of sands and stuff like that. So yeah, look him up. He's got a lot of good
But
stuff.
do some of the numbers you were showing today, does that somehow relate to like what you might expect when like for vehicles over like the like I don't know like the I don't know, forgive me, but it's like the shear stress you're testing,
Right.
That sort of thing. Like, does that make some prediction about how traffic would interact with the sand or?
Yeah, so shear stress is definitely one of the factors that impacts trafficability. Again, trafficability is not my field of research and not my specialty. So again, Stephen could tell you a lot more about this than I could. However, I do know that it is one of the aspects of it. Mainly for this presentation, the reason why we focused on shear stress is because with the longshore currents and then wave force and stuff like that, as well as like wind forcings, we would expect that shear stress gives us our shear resistance and internal friction angle gives us an idea of its susceptibility to erosion and kind of its ability to stay on the beach.
Okay.
Yeah, thank you.
Did any of your samples fall within the bedrock zone?
Yeah.
Yeah, so they're really, so the one transect is kind of near hard bottoms, right? And that's actually also why the beach is not getting nourished that often, because they have to go every single time through that detailed assessment of the hard bottoms. So that beach is, I think, has been nourished, but it's not like highly nourished because of the hard bottoms. But so yeah, the transect 2 is the one that goes into the hard bottoms, where you have more shell hash content, and the other one is a little bit more separated from
Yeah, I'm just curious about that drop in moisture content.
Yeah.
So maybe that's affecting it or they're related.
Yeah, so I mean, that's kind of going into what we were talking about, where the presence of this shell hash, because of either its shape or the fact that it's larger in grain size than the sand, is creating larger voids, right? And so when we have larger voids in our sediment, in our soil, what we're actually experiencing is more drainage. So the water has a place to go, draining out. So then when we're taking our little probe on the beach and doing our volumetric moisture content, we're actually getting lower moisture values because of the fact that these voids are larger.
Maybe just, I go ahead because it's kind of related. Maybe talk a little bit more about that promoting accumulation, because that's always something that intrigues me and it's directly related to talking about.
Yeah, so like I mentioned, with larger voids and voids being comprised mostly of air instead of water, what we're seeing is larger permeability of the sample, but also higher drainage. And in these drainage zones, we actually do see higher accumulation of sediment as along the beaches, and then these are zones where we typically see accumulation compared to erosion.
Because it's bigger, so bigger grain sizes, they
Bigger
are less
voids.
mobile.
Yeah.
Bigger voids, yeah, so there's more place for the
Infiltration. So if you're infiltrating,
Oh,
you're
okay,
practically pushing sediment down and keeping sediment in place, while if you're exfiltrating, you're helping erosion, right?
Oh,
So
gotcha.
everywhere
Yeah.
where you can promote infiltration,
Mhm.
you're promoting accumulation. And so that makes it such an interesting point, because that would suggest that the shell hash is actually helping quite a bit to against erosion from swash, for example, right? Swash is a great example where it runs up, and if it just immediately seeps in and keeps sediment really nicely on where it is, while if the swash is really going up and down, it erodes pretty rapidly things, right?
So your shear stress, is that like what a wave would essentially put on it? So is that comparable to what average wave would push?
So well, okay, so that's a kind of a different study in terms of what we actually see in these hydrological conditions or hydrodynamic conditions. But yeah, so when we're talking about bed shear stress and bed shear stress resistant and resistant to erodibility, what we look at a lot of times is, our wave action, our wave energy, as well as the current. So those both can inflict shear forcing on the bed. For this specific beach, we didn't do a hydrodynamic study. This is kind of just generally more focused on the geotechnical aspect of it. But yeah, that's a very good point. That would be kind of a really good companion to this, just to look at what the hydrodynamics are like in this location.
So, what do you guys have a question?
Keep
Questions that you are,
I mean, I enjoyed the presentation. Do you recommend that, I guess, across Florida, since we're trying to save our beaches, should we include shell hash in their construction?
Yeah, so it's a great question. And from conversations I've had with people in industry and dredging, a lot of times shell hash is usually just considered large shell fragments. And it's not really considered on a whole as maybe like the smaller parts and the smaller grains. So that's, again, another reason why I want to look into further, whether this is actually an impact of the shell hash and the shape of the shell hash, like grains individually, or if it's more just the fact that we're seeing that the grain size is larger with the shell hash. But yeah, so if we can, say that, hey, the shell material is increasing these properties and helping with accumulation, then yeah, I think it makes sense going forward to include that more when we're doing nourishment projects.
You had a question?
I was just gonna ask, is the shell hash here derived from the hard bottom outcropping or outcropping in the near shore, or is it completely separate?
Yeah, so the outcroppings are bedrock. So it's slightly different materials. The shell hash, this comes from, shells that come from marine critters and stuff like that, and then are brought on shore. And so the reason why we figured that there might be accumulation around these hard bottoms is they kind of act like a natural groin where they would collect sediment and specifically larger sediment.
Maybe Andrew, you know actually better if you would have some of these, like shell, different critters with shells. Are they settling typically on these hard bottoms? I mean, we found the shells all around,
Right.
but we didn't really see like animals or so stuck to the hard bottoms. But so I guess that's the question, right? Are they just trapping the shell, or are they producing the shell just in a
Yeah.
different season? What could also be?
Yeah, so I've looked around those a little bit, and what I recall is that there's barnacles, which will produce calcium carbonate tests that could fall off and contribute. And I don't know, what kind of quantities there are there. There's also snails
Yeah.
that are out there as well, and they would also contribute. My understanding is that a lot of the calcium carbonate, like shell contribution to the sand on the beaches here is coquina, and it's a bivalve.
Yeah.
And I don't know how much of, I don't know what proportion of them are like living like right in the kind of beach kind of swash zone versus like further offshore and maybe being sourced through nourishment. But I was under the impression that was like that kind of yellowish color to the sand that's really common in that stretch of coastline is the coquina shell, which could be locally produced, but it's not necessarily hard bottom like origin.
Yeah, makes sense.
They may aggregate around
Yeah.
hard bottom, but
Yeah.
I think that's been a safe thing. But that's, I haven't like directly like looked into that, so.
That would be kind of
Yeah.
cool to figure out too, right? Because I mean, there was no doubt, you can very clearly measure that there's more shell hash around those guys, the hard
Yeah.
bottoms, right? But again, we wouldn't really know where it's coming from, right? Or how it was.
Yeah, I guess I kind of would have thought it'd be kind of like, I mean, I think it was like when you pan for gold, like you have like, there's certain ways like collect gold from like a river, like from gravel, right?
Yeah.
Like they typically are like, it's a pan that has like little ridges in it, or like a sluice that's got, also catches the denser gold. And I kind of thought that those hard bottoms, because of these like parallel ridges, are kind of catching denser, just accumulating stuff in the same way. But,
Yeah, absolutely.
Good questions online. If someone online has a question, put it in the chat or raise your hand.
We might need to make sure the speaker's on. Of the
Oh, the
computer.
speaker for the computer?
Yeah, if you wanna. We weren't hearing it.
Is there a camera in here right now?
Yeah, there is.
Oh, it is there, okay, yeah, I think
You're on
I think-
camera.
they used to have I was looking, I think they used to have a different camera that's not.
I mean, no one has spoken up, but.
You know, you might have identified an interesting trade-off in that shell hash might be good for beach nourishment, the city wash away, but it's also less desirable. And I know if you live on a quartz beach and then it gets eroded and they put shell hash back on it, everybody's disappointed.
Sure.
Because it sticks to you and it actually might lower property values, but you know what? It
Maybe they like,
protects them more.
yeah, maybe they like it more if there's more beach. Right?
Yeah, it doesn't cost as bright, yeah, so, yeah.
And then if you're also comparing that to like more hard engineering solutions,
Yeah,
I'd say that probably
You know,
presence of shells is probably
sure.
more desirable
I'm
than
sure you
walls
could
and-
quantify- I'm sure you could quantify sort of the willingness to pay or, you know, how much people value that when they know the difference, yeah.
Great.
Yeah.
Is there any other
Looks like
questions?
there's one in the chat maybe.
Okay, yeah, that's
Let's just Sharon saying great job.
Oh,
No.
okay. Thank you, Karen.
Okay, so do you want to speak a little bit about the student club before we
Yeah.
go to some announcements?
Absolutely, I'd love to speak about the student club. So yeah, one of the things that I have the joy of doing here as a PhD student at UF is kind of co-leading the student club with Leah. And so what we're trying to do is we're trying to just build up communication and connection between students in the CCS kind of broader community. And so CCS is a very broad kind of multifaceted. We've got a lot of people that are more biology. We've got some engineers. I think there was a landscape architecture student that was in one of our meetings. So we've got a nice broad array of different backgrounds. And so what we're trying to do is we're trying to bring students together to collaborate on potential research projects, collaborate on poster presentations, and just kind of work together and have a little bit of a stronger community. We're also doing a lot of community outreach with the local community. A couple of months ago, we did a Howard Bishop STEAM night where we had a little stream table up there and so did some outreach for the local community. And actually coming up on June 8th, we will be at the Tower Road Library as part of the Alachua County Library District National Ocean Day. And we'll have a couple booths there as well. So yeah, what we're trying to do is we're trying to get a little bit more out in the community, start collaborating with the community, but then also kind of bringing people together and trying to, spur and start research opportunities here at UF.
Yes.
Thank you.
Thank you. Any questions for the student club? No, not right now. I have a couple of announcements that I would like to share. So So speaking about the student club, so the student club has actually taken over organizing and managing our CCS monthly social. Thanks for that. And that is coming up on June 5th, 5 p.m. at Cypress and Grove. And this time the theme is board games. So I'm really bad at board games, but I'm sure there's plenty of people who are really good at them. I have like some favorite ones. So bring your favorite board game and join us at Cypress and Grove, June 5th, 5 p.m. And maybe I'll learn something and eventually get a little bit better at board games. And then, of course, we have our next CCS monthly forum in about a little bit less than a month from now, June 18th, again, 3:30 through 4:30. The topic this time will be human perception of nature-based solution, and Professor Lee from the Landscape Architecture Department and the Florida Institute for Built Environment Resilience, or FIBER, is joining us for that. Similarly, as this time, it will be available on YouTube. However, we will not have an in-person session for that month. We will just have the remote session then. So please consider joining us then as well. And then something to celebrate. The spring semester finished and we had quite a few people graduating. So special shout out to Renee Price from David Kaplan's lab, Julie Fernandez from Andrew Altieri's lab, Juan Torres from Arnoldo Valle-Levinson's lab, then Stefano Bondi from Alberto Canestrelli's lab, and Dakota Lewis also from Andrew Altieri's lab. So congrats to you guys. Well done. We're really proud of you guys. And I think this is all we have for today. So thanks for joining. And thanks for presenting again, Noah.
Thank you for
This was
having me.
great.
Yeah.
And then I hope we see you all in a couple of weeks on June 18 or